Okay, so it's my pleasure to introduce Rylee Lyman from Rutgers University. She's going to talk about train track maps and cities on graphs of groups.
Great. Thank you for having me. So mainly I'm going to tell you about, I'm going to start by telling you about graphs of groups and train track maps and graphs of groups. I probably will tell you what the words CT mean, and that's about it, for which I'm sorry. The definition is a page, so maybe you don't want to hear it anyway. I'm assuming that most people have seen graphs of groups maybe before. So hopefully this is like a little bit of a review, but you probably have not seen it quite this way. So let me explain my idiosyncratic way of viewing graphs of groups. So if I have a graph G, it determines a small category G. So a category has objects and arrows, and the objects of my category are just going to be the vertices and edges of G. So here I have a graph. It's got 2 vertices, V and W, and 3 edges, A, B, and C. And so my small category, G, has 5 objects, 1 for each of my 2 vertices and 3 for each of my 3 edges. And then there are the non-identity arrows of my category go from the edges to the incident vertices. So the edge B is incident to the vertex V and the vertex W. So I have an arrow from B to V and an arrow from B to W. And similarly, the edge A is incident to V twice. So I have 2 non-identity arrows, both from A to V. And then similarly for C. So here's my small category. So I can play this game for any graph. Great. So what's a graph of groups then? So a graph of groups is, it's for us, all of our graphs are going to be finite. Connected is a little bit more important, but we'll just assume finite and connected graph G. And a functor from the small category to the category of groups with arrows, injective homomorphisms. Okay, so that's a lot. In English, what does this say? It says that I have, for each vertex V and edge E, I have groups. I'll call it fancy G sub V and fancy G sub E. And the functor tells me that for the arrows in my small category, I get injective homomorphisms of groups. So injective homomorphisms from, so we'll call that maybe iter sub E, from fancy G sub E to its terminal vertex and also to its initial vertex. So I'm writing tau for the terminal vertex, and I'll write tau E bar. Sorry, this should be E for the initial vertex. So here was my small category from the previous page. And what I've described for you in this big figure is a graph of groups. So associated to the edge B, I give the group just the trivial group. Associated to the edge A, I'm giving the cyclic group of order 2, and associated to the edge C, I'm giving the group Z. And then the vertex groups are the Klein-4 group on the left for V, and the free group on 2 generators for W. And then I have to describe injective homomorphisms. So from the trivial group, I mean, there's nothing to describe. There's only one homomorphism, so that's fine. And then from the cyclic group of order 2 to the Klein-4 group, I have one setting. So I'm saying that the cyclic group of order 2 is generated by G, and that the Klein-4 group is generated by A and B. And so I'm setting G to A for one of my homomorphisms and setting G to B for the other. And then for my my other guy, I'm saying the generator of Z is T, and I'm setting T to XY both times for both of my homomorphisms. So that's allowed. I can have different homomorphisms or the same one if I have a loop. Okay, great. Okay, so that's a graph of groups. Again, hopefully this is somewhat review. More review, I guess, is the fundamental group, the fundamental theorem, I guess, of Basser theory says that oh, sorry, let me just process what's on my slide first. Okay, so given an action of a group F on a tree T that is without inversions and edges, which just means that for all E, there does not exist a group element G such that G sends E to E bar. So it doesn't, flip the edge. That's not allowed. So given a group action of a group F on a tree T without inversions and edges, there's what's called a quotient graph of groups. So a graph of group structure on the quotient. I can give it, I can describe it a little bit, I guess. So maybe here's T. Here's the natural projection to the quotient. So G equals the quotient of F by T. And inside of T, I can find a fundamental domain. So fundamental domain, I'll call it T naught, I guess. The point of the fundamental domain is that it contains one edge for every edge of the graph G. So one edge for every quotient. I guess inside this fundamental domain, I can take something that projects to a spanning tree for G. So if S inside G is a spanning tree, so a tree that meets every vertex of my graph G, I can lift it. So maybe I'll draw a picture. So maybe my graph looks like this. And maybe my tree, who knows what it looks like? Maybe it looks like this. Maybe this is like infinite valence, who knows? So maybe my fundamental domain contains one edge for each edge of the quotient. And maybe my spanning tree S is this spanning tree. There's only one spanning tree for this graph, so that's fine. So maybe this is supposed to be my S tilde in yellow, lifting my S, and in blue is my T naught. So what I do is I say that the edge group is the stabilizer of the lift of my edge E in T naught. And I say that my vertex group V is the stabilizer of the vertex that lives in S tilde. So it's the stabilizer of V tilde in S tilde, both under the action of F. And if I'm lucky, so I need also inductive homomorphisms between the edge groups and the vertex groups, and I'm gonna mostly sweep that under the rug. If I'm lucky, what it is it's the inclusion of the stabilizers into the stabilizers. And if I'm not lucky, then I have to conjugate by some element of the group to make it work out. So you just have to like line up. So maybe this is I have something that stabilizes this vertex, and I need to make it stabilize this vertex or something. So I can just conjugate by an element of my group to make that happen. Cool, great. Okay, so that was maybe a bit more than I should have said about quotient graphs of groups. I'm sorry. Okay, anyway, the point is the main theorem of Basser theory says that every graph of groups arises as the quotient graph of groups from a group action on a tree. So every graph of groups span to G really comes from an action of a group F on a tree T. The group F we call the fundamental group of the graph of groups G, and we call the tree T the Basser tree for the graph of groups. The fundamental group of the graph of groups really deserves its name. You can think of it as being so there's really a vertex, like not a vertex, a base point, which I'm going to take to be a vertex, I guess, for convenience. And you can think of elements of the fundamental group of the graph of groups this way. So you can think of them as edge paths. You start with a vertex group element, then you take an edge of the graph, then another vertex group element, and then another edge of the graph, and then so on and so forth, all the way up through, I guess I started with G naught, so I'll finish with GK minus 1, EK, GK. Let me really quick go grab my graph of groups from before. Here it is. Sorry for the whiplash. Here I am, I'm grabbing it, copy, awesome, paste, wonderful. This is associated to the graph. I guess it had a vertex V, a vertex W. I called this edge B. I called this edge A. And I called this edge C. So an example would be maybe something like, so maybe I'm basing my fundamental group at V. So maybe I could go out across the edge B. So I could do B. Let me orient my edges. Sorry. Okay, so I could do B and then pick up an element of F2. Oh, it's laggy. Okay, that's not good. I could do B. I could do G and F2, or maybe not. I won't call it G. I'll call it X. Fine. X, Y, X inverse even. Like I can do some word right in F2, and then maybe I'll go along B. Sorry, C. The edge C. This edge here, and then maybe I'll just come back along B. So that's a perfectly fine loop in my fundamental group of this particular graph of groups. Cool. All right, so I'm going to tell you what so Bass of Bass and Sayre defined something called a morphism of a graph of groups. So I'm going to tell you what it is now. But first, I need to tell you what a morphism of graph is. So there's like secretly, I'm not going to get like too, I don't know, technical with it, but secretly there's like a combinatorial category of graphs, and these are the arrows in that combinatorial category of graphs. So what it is, a morphism of graphs is I'll say a continuous map. Oh, I guess that actually is implied by, sorry, this bit preserves adjacency. Okay, so it's a continuous map, sending vertices to vertices, edges to edges, and preserving adjacency. Okay, great. So you can send edges to edges or vertices. Yeah, so you can. It's a continuous map that either sends faithfully edges to edges or it collapses them to vertices. So those are the two things that are allowed. And a morphism induces a functor between the associated small categories in hopefully the evident way. The edge objects get mapped to the edge objects or vertex objects that they get mapped to, and the homomorphisms, or the arrows, I guess, sorry, get mapped where they get mapped. Okay, fine. So that's a morphism of graphs of groups. Sorry, of graphs. What's a morphism of graphs of groups? Well, if a graph of groups is a functor, then a morphism of graphs of groups should be some sort of natural transformation of functors. In fact, it turns out the right definition is a pseudo-natural transformation, which is just more words for which I am sorry. but let me just sort of, there's a diagram that commutes. It's a square. Let me draw the square. So you have an edge group, and it includes into a vertex group, like so. And it's getting mapped by my map F. So there's a homomorphism of groups from G of E to G of F of E. Fancy G prime, I guess, of F of E. So this is the edge group that I started with, and this is the group that it's in the morphism. The edge E is getting either sent to a vertex or to an edge. Let's assume it's an edge. So this is the edge group that it's getting sent to. And then that includes into a vertex group. Okay, fine. And I also have homomorphisms from my vertex groups. Great. And here's the inclusion here. And this diagram, if I were to write just the inclusion of F of E into tau of F of E, I wouldn't be quite right. It turns out that there's a conjugation that you have to sort of twist by. So I'll write it like this. So add delta E, whatever that is it supposed to be the inner automorphism that sends X to delta E X delta E inverse. So it's the inner automorphism that's conjugation by delta sub E. So delta sub E is part of the data. So in other words, in English, there are homomorphisms from edge groups and from vertex groups. Oh, sorry. And there are these sort of twisting elements. Delta E for each oriented edge. So for E, an oriented edge of fancy G. Okay. I'm going to give you a way to think about these twisting elements in just a second. But first, the thing to observe is that a morphism of graphs of groups induces a homomorphism of fundamental groups by the rules. So if I have an element of a vertex group, it gets sent to that the image of that thing under the map F sub W. And if I have an edge, it gets sent to, well, the image of that edge, and then followed by the twisting elements, delta sub E bar and delta sub E inverse. You can check, it's not too hard to check. If you want to stop paying attention to me, you should maybe sort of try and assemble what I just said and check that this really does give a well-defined map on the fundamental group. Great. But it actually, Bash shows it gives us more than just a map on the fundamental group. Given a morphism of graphs of groups, so F from fancy G, so with taking a base point V to a base point W, there's a unique morphism of Bass-Serre trees such that the following diagram commutes. So if I do the natural projection and then the morphism of graphs of groups and do the morphism of trees and then the natural projection, I get the same thing. And what's more, this morphism of trees is sort of F sharp twisted equivariant. So if F sharp is the map on fundamental groups, what I get is that F tilde of gamma applied acting on X is F sharp of gamma applied to F tilde of X. So there's a way of lifting these morphisms of graphs of groups to twisted equivariant morphisms of trees. And here's maybe where to think about the twisting elements, or maybe on the next slide, I guess. The other thing that you can do is that you can go the other way. So if you have a map, a homomorphism of graphs of groups, fundamental groups of graphs of groups, let's call it phi, and a phi twisted equivariant morphism of Basser trees, then there's actually a morphism of graphs of groups such that the diagram commutes. So the elements delta sub E, maybe you could think of them as so over here on gamma, I have a fundamental domain. So maybe my graph of groups looks like this. And maybe this graph of groups looks like, maybe it's a rose on 3 petals, I don't know. And maybe it has a fundamental domain over here, but maybe this vertex for some reason has like more valence. Maybe I should draw those in a different color, so I will. So maybe there's some good reason for it to have a bigger valence. And maybe the morphism of graphs of groups sends this guy here. Like maybe it matches up one of my edges and it fails to match up the other one. So the elements delta sub E, they sort of record the failure of F tilde to match up fundamental domains. But the point is, these choices of fundamental domains in the Basser tree, they're not really unique, even if you choose a vertex to include. And so that also tells us that the morphisms are also not quite unique. You can kind of alter the twisting elements delta sub E and also the vertex group and edge group homomorphisms kind of up to conjugation. So they're sort of well defined up to conjugation. And there's like it's not hard to write down like the exact things that take one to the other, say. Okay, great. All right. So I'm interested in outer automorphisms of free groups, among other things. And I was also interested in outer automorphisms of fundamental groups of graphs of groups more generally. So what I was wondering is there a way to sort of extrapolate from this notion of a morphism of graphs of groups to something more like a map? So a map of graphs of groups should allow you to not just take edges to edges, but maybe more generally to allow you to take edges to edge paths, say. So that's what's going on here. So let's have two groups F and F prime be acting on trees T and T prime. And let's suppose we have a homomorphism between them, F to F prime. So an equivariant homotopy between phi twisted equivariant maps, F and F prime from T to T prime, is a homotopy F sub T such that each of the F sub T's is itself a phi twisted equivariant map. So it's sort of exactly what you want it to be. So every phi twisted equivariant map F from T to T prime is homotopic to one that becomes a morphism after you equivariantly subdivide edges of T. So what's going on here? So one thing that might not be true about either of the maps, the map F, I guess, as you start with it, is it might not send vertices to vertices. But I can just sort of wiggle things by an equivariant homotopy so that now it does send vertices to vertices. So that's fine. And then maybe it doesn't send edges over edge paths. Maybe it does something silly. Like maybe it sends an edge over like just a teeny bit of an edge and then it backtracks, and then just another teeny bit of another edge, and then it backtracks, and then it like a genuine other edge, and then little backtracking. But up to homotopy, I can straighten that out. So I can straighten that out into just take an edge, take another edge, take a third edge. Don't be silly. So yeah, that's my equivariant homotopy. And this map here, if I equivariantly subdivide, say this is the image of this edge here. If I subdivide this edge into 3 edges, 1, 2, 3, now the map is a morphism because it takes edges to edges. So that's the general picture. After, like up to equivariant homotopy, you have a map that becomes a morphism after you subdivide edges of T. We already know how to like project morphisms of graphs of groups to the morphisms of trees, equivariant phi, like twisted equivariant morphisms of trees, to morphisms of graphs of groups. So if we have a map that becomes a morphism after you subdivide, we have a way to project that to the quotient graph of groups as well. It turns out the actual conditions that you need to write down are a little bit fiddly. So I'm just not going to tell you them. I hope that's okay. So this latter kind of phi twisted equivariant map that becomes a morphism after you subdivide equivariantly, I'm going to call that a map of graphs of groups. And then equivariant homotopy of phi twisted equivariant maps upstairs has a combinatorial shadow down in the graph of groups. Basically, the things that you're allowed to do are you're allowed to change the image of, so an edge goes to an edge path, you're allowed to change that edge path by a homotopy. Okay, so that's fine. And then you're also allowed to kind of pull vertex groups across edges. It's vertices, sorry, across edges, provided that the image of the vertex group really allows you to do that pulling across. So I wrote down an example of a map of graphs of groups. There's no particular reason to be interested in it, but let me just sort of tell you a little bit about what's going on here. So the edge E gets sent to the edge path that starts by taking the element A in this vertex group. Then it goes along E and then along F. And then it picks up an element C in this Klein 4 group. Then it comes backwards along F and then it goes along G. So like that. The edge F gets mapped to G bar F. So this vertex and this vertex are fixed, but this vertex here is getting mapped to this vertex here. And in fact, the whole edge G is getting collapsed to a point. It's this point. The edge H is getting mapped over the edge path H. Pick up the element of the cyclic group of order 2, B, and then G bar, and then E bar, and then I bar. So like that. And the edge I is getting mapped to over I, and then pick up A cubed, and then go along E, and then G, and then I again. So I don't, this is just like an example to write down, just so I had one. Great. Okay, so fine. So if I want to study outer automorphisms of fundamental groups of graphs of groups, it would be nice if I had a particularly nice class of maps to work with. So I'm going to tell you about what that class of maps is now. So a map between graphs of groups is a homotopy equivalence if, it's exactly what you think it means. There's another map, G prime, from fancy G prime to G. So going back the other way, says that GF and FG are both homotopic to the identity. A homotopy equivalence is a topological representative if, in addition to mapping vertices to vertices, which is already baked into my definition of a map of graphs of groups, it also has to send edges to non-trivial tight edge paths. So non-trivial meaning contains an edge, and tight meaning it can't be made shorter by a homotopy. So these are sort of the combinatorially nice maps that I'd like to work with. Okay, cool. So I think, okay, awesome. So given a graph of groups G, you can ask, okay, so given an outer automorphism, does it admit a topological representative? It turns out this condition gives you a subgroup of the outer automorphism group of the fundamental group of your graph of groups. I suggest the name like the modular group or the mapping class group or the graph of groups for this. I think that's a cute name for it. You don't have to go with me on it, but I'm going to use that for this talk. So in some cases, the mapping class group of the graph of groups is all of the outer automorphism group of the fundamental group. So this happens. So in the language of, if you happen to be familiar with it, Girardel and Levitt, what you want is a sort of canonical deformation space of the Basser tree to live in. So let me just give you some examples. So maybe the fundamental group of your graph of groups could be virtually free, and your graph of groups could have finite vertex groups. Great. In that situation, every outer automorphism of your fundamental group can be represented as a topological representative on this graph of groups. Maybe your fundamental group G is just a finitely generated group G, and G could be a graph of groups with trivial edge groups. So this would be like the Grush code decomposition of a finitely generated group as a free product. So every finitely generated group G has one, and this ends up actually being respected by the outer automorphism group. And maybe also more generally, you could have, or maybe not more generally, just in a different vein, your fundamental group could be what's called a generalized Baumschlag-Solitar group, and your graph of groups could have all of the vertex groups and edge groups be isomorphic to Z. Being the fundamental group of such a graph of groups is the definition of being a generalized Baumschlag-Solitar group, in case you're not familiar. Okay, cool. So what I'd like to do is study outer automorphisms of, say, these groups, but also maybe other groups as well. Oh, here's another example. Okay, cool, great. I'm going to come back to this one though. Let me tell you my results first. So I have two theorems to tell you. This first one actually can be upgraded a little bit. So let G be a graph of groups with finitely generated co-Hopfian edge groups. I'll tell you what co-Hopfian means in a second if you don't remember. But what else is to say? So this is maybe one hypothesis that you could have. Another hypothesis, so I'll say two, is that your vertex groups are finitely generated, and your edge groups have finite index in the incident vertex groups. So that's another possibility. So under either of these two assumptions, every outer automorphism that admits a topological representative is represented by a particularly nice topological representative called a relative train track map. Relative train track maps were introduced for outer automorphisms of free groups by Bestvina and Handel in 1992. I think maybe I will attempt to tell you what a relative train track map is. I think that would make a good place to go. If your automorphism happens to be what's called irreducible, then what you get is even better. It's called a train track map. I will definitely tell you what a train track map is. So some things to note about this theorem. For free products, this theorem is not new. It was first done by Collins and Turner in '94, and more recently by Francaviglia and Martino in, I think, 2015. I could be wrong, using kind of different methods, but they both give relative train track maps for free products. Another case where So certain, I'll say all, but it was really certain virtually free groups was done by Sikiotis in 2004. His situation was he wanted his edge groups to be finite of the same cardinality. So one way to think about these two assumptions is there are different ways of generalizing the trivial group. So being a group is co-Hopfian. Gosh, I have so little room on this slide. A group is co-Hopfian if every self injection, so an injective map from the group to itself, is in fact an automorphism. Finite groups are co-Hopfian. The trivial group is co-Hopfian. And so maybe one way of thinking about this first condition is that you're generalizing your edge groups being trivial to your edge groups being co-Hopfian. The second condition here, this second condition is really cooked up to capture generalized complex Holotter groups. Well, in the second condition, if your vertex groups are trivial, then certainly your edge groups have finite index. So that's having your vertex groups be non-trivial, but your edge groups still having finite index is like maybe a generalization of being trivial, I guess, in that way. Okay, great. So my other theorem, which I don't think I will tell you much about today, is if your graph of groups has trivial edge groups, so that means that your fundamental group is a free product, then every outer automorphism that has a topological representative has a positive power that is represented by a particularly nice kind of relative train track map called a CT. CT stands for completely split, I think improved maybe, relative train track map. I don't know how it stands for this. I don't know where the T is T coming from train track and C from completely, I guess, or maybe C from completely and T from split. I have no idea. I don't know. Anyway, so this is originally done by Feighn and Handel for out of N in 2011. Cool. By the way, the title of my talk is the title of a paper on the archive. I would not suggest you read that paper because it's being revised currently, and it's going to split in two. This will be paper 1, and this will be paper 2. So this will be called this theorem that this paper will be called train track maps on graphs of groups, and this will be called CTs for free products. Great. Okay, I think that's everything I wanted to say on this slide. Let me tell you what a train track map is. Great. So let's give ourselves just a graph. Okay, so not a graph of groups, just a graph. So a homotopy equivalence of a graph is a train track map when it sends vertices to vertices. Okay, good. And the restriction of any power or any iterate really of my map to an edge of my graph is an immersion. So the idea is there's no cancellation in the images of edges. I have 2 examples. This one here, it's maybe not so hard to see that this is a train track map. So what the map does is it sends the edge A over the edge B, and it sends the edge B over the edge path B followed by A, so like that. And the point is there's all sort of positive orientations. So no backtracking could occur. So no matter how much I iterate the image of a single edge, I'll still get something that's like immersed. So that's good. This thing over here is maybe a little bit more complicated. So here's what it's doing. It's sending the edge A to the edge C. It's sending the edge B to the edge D. It's sending the edge C over B bar. So there's like a flip happening to like part of what's happening here. The edge D is getting mapped over the edge G, the edge path G, E, F bar. And then E is getting mapped to A bar. F is getting mapped to G bar, B bar. And then G is getting mapped to F bar, B. So it turns out there's like a finite dynamical system that you can attach to this map that allows you to check that what you have is a train track map. In the interest of time, I guess I won't go through that check. It's not so bad. Basically what it does is you look at pairs of edges with the same initial vertex, and you define a map on the set of those things. So maybe A would go to C. So this edge here, this oriented edge would go to this oriented edge, and B would go to D. So that I get a map from this pair of oriented edges on the left to this oriented pair of edges on the right. And I can sort of iterate that process. And if I never collapse two distinct edges to the same edge, what I have is a train track map. In case you're curious, this happens to be related to a pseudo ANOSA 5 braid. Here's the 5 braid. It's sigma 1, sigma 2, sigma 3, sigma 4, sigma 1, sigma 2. It's a result of Ham and Song. That this is the pseudo ANOSA 5 braid with the least dilatation. Secretly, what I did was this graph right here, it admits a hyperelliptic involution. You could imagine taking the graph, picking it up, and flipping it over. Something that's cool is that the map that I described over here respects that hyperelliptic involution. So it should descend to a map on the quotient graph, or really the quotient graph of groups, because the involution has fixed points. And so really what I did was I found a train track map on that quotient graph of groups, and then I just lifted it up to the double cover. So I don't know, I think that's fun. So that's a little bit about train track maps. With my couple minutes left, let me try and tell you what a relative train track map is. Oh yeah, so sorry. So I just said in words what happened here. Here's the hyperelliptic involution. Here's the map of graphs to groups that you get. Okay, cool. The definition is the same, by the way, but immersion has to be understood in the graphs to group sets. So for example, down here, the edge F, its image is F, B bar, pick up the non-trivial element of the cyclic group of order 2, and then come back. So you have to say that, okay, that's somehow an immersion, or it's locally injective because of this vertex group element. Okay, fine. Okay, great. Not proof ideas. What is a relative train track map? So a relative train track map, the idea is sort of, there's an algorithm that you can run on a topological representative that tries to improve it to a train track map. It has a fail state, and it fails if it finds an invariant subgraph. So if it finds an invariant subgraph, it fails, great. So the idea of a relative train track map is to allow invariant subgraphs. So relative train track maps. The idea is to allow a nested sequence So I'll start with the empty set. I'll go up to G1, G2, up to Gm, say, equals G of F invariant subgraphs. I'm going to be a little bit cagey about whether I'm talking about graphs or graphs of groups. If you'd like to just think that I'm talking about graphs, that's fine. The definition makes perfect sense for graphs of groups as well. These invariant subgraphs, they don't have to be connected. But each one should contain, like, they should be really there should be proper nesting. Fine. So you can talk about kind of what do you add at each stage. So the rth stratum, H sub R, is closure of, whoops, sorry. No, I don't want to paste. I would like to just write GR take away, GR minus 1. Oh, I already said closure in words. So it's all of the, it's the subgraph that you get when you just take the edges that are new. So the filtrate, so this is called a filtration. You can associate a matrix to your map of graphs. Maybe I won't describe how it happens, but the idea is you just look at, you take an edge, you look at its image, that's an edge path, and you just sort of write down, okay, it crossed these edges these number of times. So that's how you get the matrix. It's called the transition matrix. So the filtration is maximal when each transition submatrix. So the submatrix that you get when you look at just the edges in the rth stratum, going over the edges in the rth stratum, is irreducible, which is a nice property for a matrix to have, or 0. Okay, cool. So I'm teaching linear algebra this semester. In fact, I just barely came from teaching it to give this talk. And something that I wish we covered was the Perone verbenius theorem, which says that an irreducible matrix A has a largest eigenvalue, real eigenvalue, lambda greater than or equal to 1. And this eigenvalue, so this eigenvalue is associated to the irreducible matrix A. It's called the Perone Frobenius eigenvalue. If like I'll call it lambda sub r, the eigenvalue associated to the rth stratum is greater than 1, then we say HR is exponentially growing. And being a relative train track map is basically there are three conditions on exponentially growing strata. So let me tell you what they are. So the relative train track map. This is a brave thing that I decided to do. I don't know why this is what I decided, but here we are. So the first condition is that if I have an edge E in my Rth stratum, the edge path f of E begins and ends with edges of HR. So it's kind of, this is more a convenience than anything, that first condition. The second condition is also more a convenience than anything. If gamma is a tight path, with endpoints in the intersection of HR with GR minus 1. So that's like a finite set of vertices. Then f of gamma is homotopically non-trivial. Rel endpoints. Okay, fine. And the last condition is really the important one. It says that if E is an edge of HR, then f to the k of E. So there might be some cancellation, some backtracking in this path, f to the k of E, but it never has any cancellation in HR itself. So what does this net you, these three things? Well, it says if I have an edge of an exponentially growing stratum HR, then the edge path f to the k of E, it looks like this. So you have like stuff that happens in HR, and then you have stuff that happens in GR minus 1. Who knows what happens? Maybe there's even backtracking. So maybe I'll draw some backtracking. But there's not so much backtracking that it goes away entirely. And then, so that this is HR, this is supposed to be GR minus 1. GR minus 1, HR. So the relative train track map condition says basically that you really do see this exponential growth of lengths of paths in like at least relative to HR. So the number of edges that happen to be in HR grows exponentially. And if you just sort of forget about what's happening down here, you get actually in a precise sense. So let me sort of say like proposition. If you have a relative train track map, I'll say this and then shut up. A relative train track map, then and the top stratum is exponentially growing. If you collapse each component of the next highest stratum, you get a train track map. So in a sense, a relative train track map really is like a relativized version of a train track map if you allow yourselves to collapse down from a graph to a graph of groups. Or from a graph of groups to like a collapsed graph of groups even. Yeah, thank you.
Thank you very much, Rylee. Are there any questions for Rylee?